Hi, welcome back to the machine learning course. Today we are talking about the linear regression. And it's always good to know how did we get here. So we started with the AI in general, then we talk about the narrow AI, and then as part of narrow AI, we talk about the machine learning, and then we have learning paradigms under the machine learning, and one of them is supervised learning. And one way of supervised learning is regression, and one way to do regression is linear regression. I have videos, uh, an introduction to AI, an introduction to ML, and an introduction to supervised learning that you can watch if you want to know how we get here. But linear regression, in nutshell, is when we have data points, several data points, and we want to fit a straight line to these data points. And what are these data points? The data points are um, from the pairs of input outputs, as we mentioned before. So in supervised learning, we have pairs of x and y, which is our input and output. So the data points are the space that have this input and output together. So for example, if our input is one dimension, like here, and then y will become another dimension, then it will become a two-dimension space, and we can plot our points in this two-dimension space. Each point has a x and has a y. So for each of these inputs, we have an output recorded in our data set from our historical data. So for example, here for 4, the output is 10, for 2, the output is 5, and so on. And you can see the data points themselves, it's impossible to have a line, straight line to pass through all of them. So we want to find a straight line that fit the most to all the lines. And how we do that is, if you look at this graph, we have this blue straight line that is our uh, perfect match. And each data point has a distance between the one that is recorded and the one that is predicted. And these are shown by these little green lines, and these are the errors of our model. So this blue line is our model. These are our data set, our data points, and the green lines are the difference between the model and our data points. And this is the best we can do, right? If we move this line somewhere higher, then the the errors, the difference between the blue line and the red dots, gonna be much more. So these blue lines need to be somewhere that these green lines become minimum. One way is to just add all these green lines, but there are better ways to minimize the error that we're gonna get to them. But in nutshell, that's what we wanna do. So we wanna have the data points, which is a combination of the input and outputs, and we wanna fit a line. This is a line in a two-dimensional space. If we have uh, more inputs, like if we have two inputs and then one output, then we have a 3D dimension, and then we're gonna have a plane there. And even if we have more uh, input dimensions, then we need to fit a hyperplane. So the line is when we have only one uh, one input and one output. So after this introduction, we you have some terminology. We are not gonna go through all of that, just what we need, and then we're gonna come back when we need them. So we have dependent variables, which is basically our output, our outcome, and the y here. These are dependent on the input, which is the x. So y is dependent on the x. When we change the x, the y changes. So that's the dependent, and then the x is independent. So second one is independent variable, and also called a predictor. So the x is a predictor here. So what does the x do? It predicts the y. So if I change the x, then it can predict the y. And based on this model, like I don't have any value for 5 in my data set. I have values for 1 to 4, but based on this model, if the x is 5, then I can go to this blue line and then predict, okay, this is gonna be 10 point half or something for 5. That's what we want to do with the linear regression. We want to predict what is the value of our outcome based on our uh, independent variables or our predictors or input, and and then we have the linear regression model, which is basically this blue line that we talk about it. We can write it down in a uh, more mathematical way. So y is equal to a fixed term plus coefficient times variable 1 plus another coefficient times variable 2, and so on. For this line that you see here is just this 3 first term. So y equal to uh, a constant plus uh, a coefficient times x that gonna like describe this blue line. And then if you have more variables, it's gonna be added those variables with a coefficient to this formula. And there is a vector way to write this, and then that constant will be inserted to the x um, matrix here, and you can see like with ones, um, which is they are representing the constant values, and then the x1. So that's one way to write it down, but we don't really need uh, to know all this, because we just want to get an intuition towards linear regression, and we're gonna just use the tools to fit the lines. And just one thing that I didn't mention here, that about these green lines. So we saw that the blue lines is impossible to go through all the red dots, but the the purpose of the blue line is to represent all these red dots, because that's the model. So to make this equation correct, we are adding this epsilon here, which is representing the error. So basically, what is this equation is saying that it's saying that each y is basically uh, these two term or further, they are describing this blue line or the blue plane or hyperplane. So you're saying that each y is this blue line plus an error, and then our description is complete. So each of these can be described as like the point that is on the blue line or on model plus an error, and we want to minimize this error to have the best fit. And so we can go further now. Uh, just in terms of terminology, uh, I mentioned already that the input can have one dimension or two dimension or more. Just for one dimension, the example that we had here, when we have one input, one output, it has like a special name. It's called simple regression. And then if there is more input, it's called multiple regression. It doesn't change anything in terms of modeling. It's just the name. We're gonna start with some examples with simple regression because it's easier to graph them and then explain the things that are happening in the linear regression. And then we're gonna go with more advanced multidimensional um, examples. And there are some assumptions to make the linear regression works well. We are not gonna go through them now because we're gonna see some examples and then we're gonna come back to each of these and we're gonna explain that how these things gonna affect the the outcome of our model. So what we're gonna do here, we're gonna start with a simple regression. As we said, simple regression means one input, one output, and um, with noisy linear data. So what we're gonna do here is that uh, uh, so 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 the linear regression is used to predict the reality that we are interested in. So, for example, the price of a house. Um, we wanna like predict what is the price of this house based on the features of the house, and that's the reality. And that reality is there are many things affecting that, and we may not be able to understand the reality completely ever because there are so many complex things going on there. But uh, uh, so so before we start with those examples, like we have an example here that we're gonna start with something that we know the reality of that. So we're gonna start with a line, and then we're gonna with a line that we already know about it, and we're gonna add some noise to it. We're gonna create our data set, and then based on that data set, we're gonna try to feed a line, and then we're gonna compare if our feeder line is uh, like compatible with the reality that we created. So this is just a practice to see how these linear regressions work. So um, uh, after that, when we understand everything, then we can go work with the real data from the real world examples, and then we try to feed a line. But for those examples, we will never probably know the reality. So just before we start the example, I forgot to mention something that these errors normally in the uh, in different examples, um, uh, like we are assuming that our data is linear. So it's basically we are saying that we assume that it's possible to fit a line to our data. And then we're gonna have some errors, like in any case. So this error is basically can be caused by two things. One is the noise. When we are sampling things, we may like sample some noise too. And it also could be because of the things that we are not modeling. So for example, this y, the relation between y and x uh, is this blue line, but it could in reality have other parameters like x2 or x3 that they are affecting the value of y, but because we are not considering them in this model, they may affect the position of the y, but since we are not considering them from the point of uh, y dependent on x only, they are falling on this green green error. So the epsilon here is both covering the noise and the things that we are not modeling. And as far as there are some assumptions uh, met, it's totally fine to consider them as such. So let's go back to our example here. The the example gonna clear up many of these things, And that's what we want to do. We want to start with a very simple example, and then we broaden the scope from there. So as I mentioned here, what we are trying to do is to create a reality that doesn't exist, and then add some noise to it, then sample the data, and then try to fit a model on top of that and try to discover that reality that we created ourselves. And as I mentioned, like this is just a practice to understand better the linear regression. And but later on we're gonna have real world examples, and we're gonna try to fit a line to the real data that we probably don't know the actual reality. So let's start by creating the data set first, create those red data points, and then try to fit a line to that. So as I mentioned before, we are trying to, that our example is a simple regression. So equation or our line equation or formula is something like x equal to a constant plus x and plus epsilon. The epsilon is the noise here. So uh, I'm gonna like assume something for all this. I need to add a coefficient here. So my line is the reality that I'm creating is that I say uh, y is equal to a constant plus a coefficient times x plus noise. And then I wanna discover the a and b from this noisy data. First, I need to assign some values here. Okay, so for example, we can put a 2.5, b is equal 1. Sigma is the standard deviation of the noise that I'm gonna add to this, and I'm gonna start with 100 data points. Okay, now I'm gonna start creating uh, my data set. I will start with a random seed. So for this, I'm using the NumPy. So I need to import NumPy as NP. So this gonna start my randomization from this seed, and then I am generating my X randomly from from a space between 0 to 1. This is just arbitrary. Um, so my X is gonna be randomly chosen from uh, a range from 0 to 1. These are real values uh, by this function, random function. And for each of these points, I also need to create a noise, and this is uh, generated by this function from the NumPy, the normal distribution, and then as we mentioned before, the sigma equal to 0.5, and then this is on the mu equal 0 because it's added to each point. And then when I have the noise, so I needed the noise, I needed the x, I have the a, I have the b, so now I can create my y. And this is the equation for y. So y is equal to a times the vector x. This is the vector x, 100 points randomly chosen from 0 to 1, plus b, which is 1, and then plus noise, which is normal distribution with sigma equal to half. And and then before we do any fitting, it's always good idea to plot the data points and see if they are how they look like. So for this, I'm using a scatter plot, which is basically putting a point or a dot for each data point, and I'm using the matplotlib for plotting. So I need to import that. So import matplotlib pyplot as plt, and now I can use the scatter. I'm scattering the x and y. X is one dimension, y is one dimension, so it's going to be a two-dimension figure. Uh, Maybe we go with red to be consistent with the image, with the figure that we have in our examples. And the label is, let's put it data points to be consistent with here, with this figure. So data points, red, scatter here. And we have the x and y generated data with noise and show. Okay, now we can run this. Uh, Run this. I'm not gonna put this code or any other codes in the description or anywhere else that you can copy paste. Uh, to me, the best way to learn is to type. So please try to pause the video and try to type these commands, and then that's how you're gonna learn. I never learn anything by copy pasting. I always need to type it many times, and then it will be set in my mind. Okay, so this is the result right now. There is no line here because we add noise, but you can see obviously the trend. It's an upward trend because our coefficient is 2.5, and then you can see that the y is going from around 1 to 3.5. When the x go from 0 to 1, which is consistent with this, it's the offset 1 obviously is there because when the x is around 0, the y's are around 1. So this is the offset, this is the slope or the coefficient for x, and then we have the sigma for the noise, and then this is normal distribution. You cannot see it very well here because the number of points are uh, not not enough. So I'm gonna do one thing and increase the numbers to 10,000 and see how it look like. Okay, it's better, but my points are too big, so I need to reduce the size of the points in the scatter. So let's do that with the s equal. Uh, we reduce the size. Okay, now it's better. Now you can see clearly that there is a normal distribution around that that line. That is our reality that we are interested in. So these points are normally distributed across that line. So you can see that trend there. I can make it more obvious maybe by adding more points. Yeah, maybe it was too much. 30,000. Okay, so now you can see like as we go further from the core of this distribution, there is less points, and then in the core there is the maximum density, and then you can see clearly the trend from 1 to 3.5, and the x is going from 0 to 1. So, for example, this is something uh, in reality that we are mimicking, that there is a relation, clear correlation between this y and this x. As x go up, the y go up. There is a slope, there is an offset, and we have these red points. We are now we are assuming that we are not aware of a and b, or sigma or any of this. We only have 30,000 data points. These are the red points, and we want to fit a line that best describe these points. And hopefully we're gonna retrieve those 2.5 and 1 in our model. Okay, so now we can continue with feeding a line to our data points, and this is done very easily for linear regression. So what you need is a linear regression function, and then this is part of the scikit-learn package. So you need to import this linear regression from scikit-learn package, the linear model. Uh, just as a note, this is one way to do linear regression with this package. I'm sure there are many more packages that do the linear regression. So, but this one gonna do the job. So from scikit uh, learn package, from the linear model module, we're gonna uh, import the linear regression, and we're gonna create a model, a linear regression model. And what we need to do is to just train this model based on our data points, which is done very easily like this. It's a model which is a linear regression fit. So we want to fit this model, which is a linear model, to our data points, and data points are described by their x and y. And then here the x is one-dimensional. We define it here, and y is here. So basically, this model gonna just fit the y and the line, a straight line to our data points. Next is to figure out from this model, after it's fit the line to our data, um, what are the coefficients of this trained model, and then we can extract those coefficients like this. And here how we can extract the coefficients and our constant from the model. Here you can see that we have for coefficient 2 index, and then for intercept, which is basically the b is called here, um, the constant, the the beta 0, also called intercept. The first index here we have 0 and then 0. These two are representing the dimension of the output. Here we only have one y, uh, but in the linear regression we could have more. Like when we are feeding, we can have multiple dimension x, multiple dimension y. So this is for the y, we have only one y, so we're gonna have only index 0. And for each y, we only have one intercept, one constant. But we could have multiple x if we have a multi-dimensional input. So for each y, we're gonna have multiple index for the x's. Again, here because we only have one dimension x, we only have index 0. So if we have x2, we could have coefficient 0, 1, which was pointing to the coefficient of the dimension 2, but here we don't have that. And then if we have the y2, we could have index 1 here for that y. So that's how we're going to extract the a and b, the coefficient and the intercept from our model, which is already fitted to the for to our data points, and then we're just gonna print them here, and we're gonna uh, compare it with the original one, the reality that we created this data points based, and then see if we are able to get to that reality. So let me just run this so far. Uh, okay, and uh, and you can see it's not bad at all. Like with the 30,000 points, we are at coefficient 2.4979, very close to this, and we have intercept 1. So one thing that I want to test here, and you can see that uh, the number of data points make a difference. So if for the accuracy of these coefficients and intercepts, and for example, if I go back to the 100 points, and let me do the showing of the graph at the end, so I don't have to close the graph. So if I run this again, uh, you can see for the 100 points, no, the points are so dim here, you cannot see them, but you can see the accuracy is very less compared to that. So 2.34 as an estimate for 2.5 and 1.1. So that's how it is. And then if I really increase the numbers maybe to 1 million, and let's run it again. And you can see the linear regression is very fast. Like there is not much difference basically between 100 points computation and 1 million computation. And here, like you can get still close to 2.5 and 1, but yeah, it's there will be some estimate here. You're never gonna get 2.5 because we are trying to fit a line to the data points which the noise was added. But as we have more data points, this gonna be more accurate. So that's the point there. So now to have a visual about our model, the same blue line that we had in the description, we're gonna know we have the A estimated and B estimated. Now we can, based on these two, just plot a line, a straight line, and that's our model, and see how does this stance compare to our data points. Let me go back to the 30,000 point, which was visually pleasant. And now I'm just gonna add another plot. Okay, as I said before, like if you need to do this yourself, please pause the video and please type. That's how you're gonna remember and how you're gonna learn. Um, and so here is the uh, you're trying to plot a line that based on the A estimated and B estimated. So we're gonna have X and Y generated based on this A and B. The X is generated like equally spaced between 0 to 1, and then Y is based on the formula AX plus B. And then we're gonna plot this. Let me change this to blue to be consistent with our description, and let's run this. And that's the model. So the red dots are our data points, and then we feed a linear regression model, and then based on that model we extract the estimated coefficients, and then we plot the lines. So this is the blue line, our um, our model for these points that is perfectly representing our reality, which we hide from the uh, from model here. Like the linear model here was not aware of the A and B. It was just was aware of the Y and X, which was noisy data, uh, and it was able to extract the A and B. So that's basically the point for the linear regression. We have a reality. We suspect that there is a relationship between a dependent variable and an independent variable, and then we plot it. We need to, and then we verify that that is the case. So here, when we plot the red dots, we say, okay, there is a trend between y and x. Definitely something is going on between y and x. And then we, based on the shape of the trend, we assume maybe linear regression is a good fit as a model. Then we easily, very easily, could feed a line with these two lines and then extract the coefficients from that model. And this is going to be our model, which is very close in terms of uh, detecting the underlying reality with our reality. So this blue line, if we have a new point, we can estimate what's going to be the the estimated y. So this is basic example for linear regression. We need to do a lot more in the future videos. We need to um, have, so this was a perfect data set. So the data sets are not always perfect, and they are not always compatible with the linear regression. So if we're gonna see that the data points, they can scatter in a ways that in no way you can uh, feed it with a straight line. That's why we need other estimators other than linear regression. But for many cases in the real life, um, things are correlated, things are, the relations are linear. So it's not like that we are not using linear regression in real world uh, cases. Actually, it's used a lot. So it's simple, and it sometimes can represent the relationship very easily and accurately. So if it's the right data set, the right problem, the linear regression can be easily used and uh, utilized for a real world problem, and we don't have to go through the very complex models. Although there are complex problems, there are complex data sets, there are complex realities that a linear regression cannot even get close to a good representation. That's why we need very complex solutions too, that we're gonna explain in the future videos.